now I am sorry about that. At D, even though the force is going down, the pulley is all the way around the same. So as wherever you are on the cable, the tension has to be the same because we don't have any friction at this point. And so if you cut this at right here, then you end up with these two cables, CAD and I guess the other one is ACB, both going up at 55 degrees, and then the other one, CB, going over here at 25. So that makes things a lot easier to solve than trying to deal with this force going down. All right, that's it. Okay, so the remainder of chapter 2 deals with 3D vectors. Identify horizontal projection, identify forces, and convert to vector format. And you can use the force plus these two angles to find the components. So just with those 3 bullet points, that's all you need to know. So, but what does that mean? So let's look at, let's stop this and go back to the document camera. And there we go. So now if we look at the document here, what I have drawn is I've drawn a force. Here's XYZ, here's my force. And now when I draw it in 2 dimensions, it actually looks like it's in the YZ plane, but it's not. It's actually more like this, it's sticking out. And so what I then do is I draw this projection. So if I were looking down from above, the Z down from the Z axis, I would see this projection here. And so another way to look at it is if I draw the XY plane, this would be again looking down above from Z, you'd see FH sticking out here. So what this does is it allows us, if we know these 2 angles, theta and phi, and that, it allows us to get our vectors into, instead of just being, F, we can now break it down into its Fxi plus Fyj plus Fzk. So it's 3 components, and that'll be important. And that'll be important for manipulating and doing other calculations. This in itself isn't that exciting. It's just a tool that you'll use in order to take this force, get it into these 3 components, and then we can do something with that. So when looking at this, if we look at force, if we want to figure what these are, first off, because this force is relative to the Z-axis, then right away we could see that F, the Z component, Fzk, is just going to be equal to F times the cosine of theta. And if we want to know what FH is the same as if we had a line here. So FH is just equal to F sine theta. So you can probably see where this is going, because now that I know what FH is here, I can relate FH to the Y and the X components of the force. So then it turns out that Fx, in this case, if you think about it, we draw our vector here, then, or another way to draw it would be like this. Then what do we have? We have Fx is equal to Fh, and that's going to be sine of phi. And Fy is going to be Fh cosine of phi. But because we know Fh is that, we can then write them finally as Fx equals F sine theta sine phi, and Fy is F sine theta cosine phi. And so with that, then now you have all 3 components, and then you can find the angles, because we know that there's an angle. There's that, which is theta y. This actually, the same angle here is theta z. And then this angle all the way around here is theta x. and you may need to find those. And the subsequent equations that are listed in the reading will allow you to do that. So I'm not going to go over them here, but this is just, again, a tool. And so let's look at an example of how we would apply that. Now, if we go, just leave this on here. So if we go to, and we'll come back to 3D equilibrium, but so here we have this tower, and in this tower you have three forces. You have the force AB, force AC, and force AD. And so you want to know what the resultant is. So we know that the resultant is just the sum of the individual components of the three vectors. So I know that if I showed you how to do one of them, you could do the other three and add them together. So for the sake of time, I'm just going to show you how to do AB. And given what we've already covered, it should be relatively simple. Now, again, I say simple, I'm not trying to trivialize this. I'm just saying is that simple doesn't mean easy. It just means that there's few steps. So if we look at the problem here, we have, this is my drawing of it. And what you can see, you guys can see my dot cam, right? Correct?
Yeah.
Yeah.
Okay. Thank you. I just want to make sure. And if for at any time the doc cam is unclear or out of focus, because that happened last hour, just holler. Please don't let me talk and you guys have no idea what I'm saying. So anyway, here we have this. And so what I've done is I've drawn in, here's theta. That would be the equivalent of theta up here, this angle. And then if we come down here, this line here is my projected force along this line. And these are feet, 12 feet, 18 feet, respective to where this point B is. And then this angle here is my phi. And so I can figure out phi just by these dimensions. And normally phi would be given to as an angle, but if not, we can find it. And it turns out that phi using tangent is just 33.7 degrees. So now we know what phi is. And because we know what this is, because we did 12 squared, we found out what this line is because it's 1812. So using Pythagorean theorem, we found this line here. So if we know that line and we know the 36 feet up, then we can find theta. So we did the same thing with tangent. We found that theta was 31 degrees. So now that we have those, we have what we need in order to calculate it. Try to do this, keep everything on the page. So these are just the angles for the other two. This would be AC and AD, which you could do, and that just shows you those. But so we know that if we want the tension in AB, or force AB interchangeable, tension AB is just going to be equal to the scalar value AB times lambda AB. And that's how we find what we need. So in this case, this could also be, this is also written as tension AB is equal to tension AB X plus tension AB Y plus tension AB. Okay, so I have my three components. So same as before, I can find my tension AB in the Z direction, scalar value, which will be this. That's just equal to negative 700, and that's because this is going down in the Z direction. So 700 is the magnitude. And then we know that this was 31 degrees, so it's just going to be cosine of theta, or negative 700 times cosine of 31. And so that gives me 600 pounds. And then if I want my TAB horizontal projection, H, then that's just going to be 700 sine of 31 degrees. And that gives me 361 pounds. So now that I have the h, then I can do the same thing as before. I know phi, and I know this, so then I just break it into x and y. So if I do that, I get tension ABX equals my tension AB horizontal, and then that's going to be times cosine of phi. And my tension ABY equals negative, because it's going in the negative y direction, tension AB horizontal, and that's going to be times sine of phi. So if we substitute in respective, we just get 361. Now, cosine of theta, you could either do the cosine of 33.7, or really, what is the cosine of theta, or I'm sorry, cosine of phi? It's just the ratio of this over that. So you could also just say 361 times 18 over 21.63, right? It's the same thing. So whatever one is more comfortable. So this ends up being 300 pounds. And when we do this over here, we get 361 sine of 33.7. We end up with negative 200 pounds. So our final vector then, TAB, and this is how you should present it, is it should be TAB equals 300 I minus 200 J plus, or sorry, minus 600 K pound. All right. And so you could go ahead then and do the same thing with this, and then you just say, you just put in TAC, its components, and then TAD, its components, and then you just add them together, and that would be your result, like that. All right. So once you get past this kind of weird angle here, it's fine. And some of the problems in chapter 3, you'll actually have to, in order to do to find the moments about points, which we'll talk about, you're going to have to do just that. You're going to have to first convert them into IJK components and then do it. But you know, there's a few examples on the homework that you can do that have practice, and once you get the hang of it, it should be pretty easy. Any questions so far? Does this make sense? So you'll see more of it in the examples. There's examples in the lecture that I posted. And so again, you'll have plenty of opportunity to practice it, but you know, practice it. If you have questions, see me in office hour. Occasionally I get some, but you know, whatever, some of you have, you know, it's easier to see than others. Some of you visualize it easier. Some of you it's harder until you write it out. So whatever works for you. Okay, so we that's 3D vectors, and then the next topic on the PowerPoint was 3D equilibrium. And so you did 2D equilibrium, where you sum the force in the x and the y, and you got your answer. And so this is similar. In 3D equilibrium, what we do is we identify all our tension vectors, and so we identify them as the scalar value times the unit vector, and then we just separate them into IJK components, knowing that all the forces in the x, all the forces in the y, all the forces in the z have to add to 0. And then at worst, we'll end up with 3 equations, 3 unknowns, which you can easily solve in your calculator or by hand, but it's kind of tedious. So let's look at an example of that. Now, this is a little different of an example. It's not quite the same as the ones you'll see in my lecture. So I want to do something a little different. But in this one, you have, I don't know why it's not doing this. Oh, sorry. There we go. So you want, in this one, you have a crate hanging by these 3 ropes. And so he wants to know is how much can the crate weigh so that none of the ropes exceeds 450 pounds. And then it gives you the coordinates of each of the points. So how do we do a problem like this? My notes good. Sorry about that. Papers everywhere. Here we go. All right, so here is our problem. And so what do we have? We have the 3 vectors where they're going. We know that TAB, TAC, TAD ought to be less than 450. We want to find the weight. So how do we do that? So we look at it as, first off, and the first thing you want to do on a problem like this is you want, what is your governing equation? Now, we didn't have a governing equation last one because we weren't really solving anything. But we know that in this case, our governing equation, sum the forces to 0, and that means that this force in BA, I use force and tension interchangeably, so I'm going to go with F in this. So FBA plus FCA plus FDA plus W all have to equal 0. All right, so that's my controlling equation. So first thing I want to do is, and after you do a few of these, I'll go quicker, but you want to convert these into their respective vectors, force vectors. So for example, let's look at FBA. We know that the force in BA equals its scalar value, which we don't know, times its unit vector. Now, if we look at, in this case, since we have points, we know that the distance RBA just equals RB minus RA, just the locations. And since that's 0, it makes it easy. So we know this is just equal to -2, -2I minus J plus 2K. Now, if we want to convert that to a unit vector, we know that lambda BA is just going to equal -2I plus J plus 2K all over -2 squared plus 1 squared plus 2 squared square root. And that gives me -2/3 I plus 1/3 J plus 2/3 K. All right, so there's that. So then the next step is to multiply through by this force. So our final force vector, FBA, then looks like this. -2/3 FBA I plus 1/3 FBA J plus 2/3 FBA K. Okay. So now you have that. So you could do the same thing for the other ones. And if you do that, you end up with FCA equals -2/3 FCA I minus 2/3 FCA J plus 1/3 FCA K. And FDA, since it's just down the I, it's just equal to scalar FDA times I. So here we have now what I've done is I've taken and I've made my 3 equations. So these are the vectors for BA, CA, and DA. All right. So I showed you one example, but you can easily do that. So in subsequent chapters, I'm not going to go through this. I'm just going to assume you know how to do this. So this is where you want to get this down, where you can just look at basically the objective is you can look at a force in scalar and you convert it to a vector form. That'll be the expectation. So what do we do now? So these questions, these 3D equilibriums, they're all the same in the sense is that now you want to break them up into their I, J, and K components. So for example, we have our I, J, and our K. So if we do that, we look at I, we get basically negative 2/3 FBA minus 2/3 FCA, and then plus FDA equals 0. And so effectively FDA equals what? 2/3 FBA plus 2/3 FCA. So that's my first equation, number 1 there. So you can read my chicken scratches. And then for the J equation, we get 1/3 FBA minus 2/3 FCA equals 0. So that equates to FBA equal to FCA. So that's my equation number 2. And then K, I have 2/3 FBA plus 1/3 FCA minus W equals 0. Or basically, you could move that over to the other side and be 2/3 FBA plus 1/3 FCA equals W. All right. Now, before you nod off, let's finish this. So again, you have the original diagram here. This is not really much need to see, but we know 450 pounds is the maximum. So through a series of, now what we can do is you can see that FBA is to FCA, so we can substitute that in up here, and what we end up with is that through a substitution, we end up with FDA, sorry, and these are all scalar since I'm not drawing a vector component of it. My pencil's having issues. So FDA ends up being equal to 2 FCA just by simple substitution. And so FBA is then equal to 2 FCA. So we know that as a result, we know that FBA equals FDA, which equals 2 FCA. Now, why this is significant once we get to this point is, remember, we can't go more than 450. So that means that this could be, if that's 450 and that's 450, that has to be 225. So now we know what these can be, right, relative to one another. We can put those values into this equation and solve, can't we? So we can solve and we can say that 2/3 of 450 plus 1/3 of 225 equals W. And so W equals 375 pounds. All right. So a little tedious, and I know I went through a little quick, but after you look at a few, it'll make more sense. But again, the idea here is just 3D equilibrium. And we'll repeat this again. So the more you understand this, it'll pay dividends in chapter 4, because we'll come back to this where you'll just take your equations, you'll separate them in IJKs, you'll solve them, you'll be done, and just rinse, repeat. So there's a lot of repetition in this class, unlike dynamics, which is a lot of different stuff. Statics tends to be fairly similar stuff, just reapplied. So it's like different flavors of vanilla. It's like vanilla bean, French vanilla, lactose-free vanilla, so forth. All right. So that's chapter 2, those 2 topics. So Wednesday's quiz, which you guys will take between 9 and 10, it'll be up, and so I'd like you to take it. Actually, it's available between 8 and about 10:30. So as long as you take it between those times, you're fine. If you want to take it earlier, that's fine too. But that quiz will cover chapter 2. So it may have a quiz, it may have a question on 3D equilibrium, may have a question on projected forces. So I would go ahead and be sure that you watch today's lecture before Wednesday's quiz. And if you have questions, of course, ask them now or see me in office hours. Okay, so now we're on to chapter 3. And going back to PowerPoint, you can see that chapter 3 is all about equivalent systems of forces. And what exactly does that mean? I'm not sure why they call it that, but what it effectively comes down to is we're looking at moments. And you remember those from when you were in physics. And so before we talk about any problems, let's just recall. So if you have, so now looking at the dot cam, we know that simple moments, if you have a point O and you have a force here, that we know that the moment about O, which is a vector, is just equal to force times distance, where distance is generally the perpendicular. Okay? We know also that you can, if you have your forces off to an angle, then it's, so I could also draw it like this, and that's theta, and that's F. So moment about O in that case would be force times distance sine theta, right? So sometimes this D will be replaced with R. So D is usually meant to be perpendicular, R sine theta, where that's R. And so we want just the perpendicular, so we put the sine theta there. Anyway, so that we've seen that before, we know that if it's going in the counterclockwise, it's positive. If the moment's going clockwise, it's negative, and we'll use that convention throughout. But it is a vector, but it's we sometimes oversee that because we know that in 2D it's always rotating either clockwise or counterclockwise around the K or the direction coming out of the plane. Now, let's say we want to find a moment in three dimensions. So let's say that we have our, so here's our 3 dimensions. We have some random force in space, F. And so F will have its IJK components. And we want to find, we'll just pick the point of the origin. And so we want to find the moment about O. So moment about O. So in three dimensions, it's going to be not so easy or not so trivial to find what that perpendicular distance is. But if we just draw a line from here to any point on the force, it's convenient. So it could be there, it could be there, it could be there, whatever. Let's say we point to point A, then we know that that moment about O, which will be a vector, is just equal to R, A relative to O, crossed with that force. Now, what I mean by A relative to O means you always go from the point to there, okay? So whatever that is. And so you find that vector, you know that vector, do a cross product on them, which you guys know how to do, and voila, you're done. And so you end up with moment about O. And if you've forgotten your cross product, it's in the book too as to how to do it. But I most of you, I'm sure, have been doing it many, many years, do it in your sleep. You can also do it in your calculator if you want. But so your moment about O gives you your I, J, K components of your value. And so that's a vector. So that's moment about a point. Now there is one other theoretical aspect. And so we can do a moment about a point, or we can also do a moment about a line. Now let's just do our same thing again. So let's draw a line here, and let's have our force here. And that's not perpendicular, it just looks like it. I mean parallel. So there's our force in space. All right, and let's say this is our line O, and let's see, it's OD. Okay, so this line OD. Now, what this represents is, if I remember that I drew a line from here to here, R, and I called that A. So I had A relative to O. Now you recall that if I wanted the moment about O, it was just R, A relative to O, crossed with that force. Now imagine that I want to know what is the moment about this line. And of course, the line contains the point O. And so the way to think about it is when I do a moment about this point, I end up with some moment out here in space. Maybe it's like that. That's my moment about O. So it turns out that this moment about O will project onto a line. And the line can be defined however you want it, but we project this onto this line. And this is, you read it in the book, it's kind of gobbledygook. They don't do a great job of explaining the math behind it. But effectively what you're doing is you're projecting this moment onto a line. And the way you do that is fairly easy, is you take this line and you find its unit vector. So line OD, I just go from O to D, and I draw lambda OD. So whatever that is, that unit vector, and it's always a unit vector, what I do is I dot product that with this moment about O. And that gives me the moment about the line OD. Now we know that if we do a dot product, that's a scalar. So this is a scalar value. So it ends up looking like lambda OD dotted with R A relative to O crossed with the force. Okay? So I'll go over examples of that in the lecture, but I just wanted to present that to you to show you. And those are the two things that we'll do. So it's just important to remember that this is a scalar and this is a vector. All right? Now, if we look at, I did put up a fairly easy example on here. If we look at this one, this says determine the moment of the force caused by 200 newtons at C about point A. And so there's point C and point A. In a problem like that, so these financial statements they send me from my broker are great for scratch paper. So, all right. So, what do we have? We have this last one. We have something looks like this, and kind of comes out that. And so we have our force going down here. anyway, you have the drawing, so I mean you can see it, but the idea is that we have this P equals 200 newtons here, and we have A here. And so what do we want to do is we want to figure out the moment about A created by the force P. So we know that's just going to be equal R, and this is point C up here, C relative to A. So that means I'm going to go from A to C, and that's going to be crossed with whatever this vector B is. And that's it. So first thing I do is I figure out what is P. So if I look at P as a vector, I can see that if I look at the distances, it's basically the scalar value of P, which is 200 newtons. And then what do I have? I know it's negative 70I plus 0J minus 100K. And then I have to make the unit vector, so I divide it by the magnitude of 122. So this leaves me with negative 114.7I minus 163.8K. Okay, so there's that. And then I want to go from A to C. That's pretty easy. R C relative to A. And that just gives me what? 0I plus 90J plus 100K. So when you set up when you're doing these problems, the easiest way, or not the easiest, but what I find is if you draw them out like this, and you just say a moment about A, and you say, sorry. And if you get in the habit of doing this, and the reason I want you to set this up like this is that what I'll do is I'll see this, M equals that, R, C relative to A, and then P, and then you set it up 0, 90, 100, negative 114.7, 0, negative 163.8. Now, if I see it like that, and then your subsequent answer is incorrect, but this is correct, then I probably take off very little, if any, because you got this part correct. And so, but if you don't draw it like that, you just leave it here, I have no way of knowing that you understand this aspect of it. So it's in your best interest on the quizzes and the exams is to show me as much work as possible. And that'll let me know that you understand the material. That's ultimately what I'm shooting for in this class. So if we go ahead and do the cross product, we end up with our answer, 90 times that. We end up with negative 14.74I minus 11.47J plus 10.32K, and that's in Newton meters. And that's our final answer. So it's a vector as we expected. Something I was going to say. Darn, escape. So at this point, you're done with this, and that's what I was going to say is chapter 3. Now we know we've been talking about if some of the forces equal 0 and all that. That's the one thing I don't like about chapter 3 is that we're really not in equilibrium, because here I've said what is the moment about A caused by this force P, and you're getting a resultant answer. So the assumption has to be that if this, whatever this is, that this attachment here at A, because this is mounted in the ground, its reaction would have to be exactly opposite of this, right? So A is applying a reaction to this post of positive 14, positive 11, negative 10 in order for this to stay there. But we don't really calculate that, and we don't mention that. So really what we're doing is we're doing, that's why it's equivalent forces. So what we're doing is we're saying, this creates a moment here, but we're not equating anything to zero. We're just saying this, what does this do to that point, but with nothing else. So if you keep that in mind, you'll be fine. In chapter 4, we get into the true equilibrium. And so if you look at kind of the class, it starts off, kind of easy, gets a little harder, and then in chapter 4, it gets easy again, and then it goes to infinite. Just goes up a bit. So beginning chapter 4 is pretty straightforward stuff. But so later in chapter 3, we're going to talk about force couples, equivalent force couple systems, but that's for next week. All right, so we're about out of time, but that's as much as I want to cover today. Any questions on anything? None at all? All right. Well, I have office hours after this if you have questions. Otherwise, I'll see you guys. Be sure you take the quiz. I will send out a reminder on Canvas, and I will also follow up with anything this week, any information. But otherwise, you have the quiz on Wednesday, and then the next homework assignment will be up, and the homework assignment is due today, I think at 11 o'clock. So that's it. You guys have a good week. Don't work too hard. Thanks.
Thank you.
Thank you.
Thank you.
Yes.